Thank you very much, Emmanuel, for the introduction. It's, of course, my great pleasure to be able to tell you a little bit about the ongoing research of my research group in the context of many-body physics of two-dimensional materials and ultracold atoms. And since it's a quite general conference, I want to give really an overview talk connecting these two fields here. So I'm leading a Max Planck research group at the Max Planck Institute for Quantum Optics in Garching, and together with my PhD students, postdocs, and master students, we develop theory at the interface of solid-state physics and cold atomic systems. What we are really interested in is systems which feature strong interplay between few and many-body physics, which can give rise to interesting new effects. And if you think, however, about what we have to do as theorists, well, if you think about few-body physics alone, we have actually very powerful tools to tackle such systems. Basically, can use wave mechanics and solve, for instance, for molecular states or their structure. On the other hand, also even in many-body physics, we are often safe or lucky, namely when we can actually describe systems using mean field theory. And in this case, we can basically map the problem onto an effectively non-interacting one. And a famous example is the BCS theory of superconductivity. However, in particular, as theorists and also as experimentalists, we are much more challenged if we enter the strong interaction regime or the non-equilibrium. In particular, in these systems, often a strong interplay also exists between few and many-body physics, leading to, however, then possible new emerging phenomena or functionalities of materials. And these are really the ones which we are interested in to explore with our group. So what are the prerequisites to actually find a strong interplay between few and many-body physics, where we can compare energy scales? If you think about few-body physics, this is determined, for instance, by binding energy of molecules. On the other hand, many-body systems are characterized, for instance, by their density or by the Fermi energy. Now, when both of those become of the same order, then actually the many-body environment can influence the few-body physics, but also vice versa. For instance, bound states influence what is going on in the many-body system. Now, in cold atoms, it's kind of actually natural to enter the strong coupling regime. So what we can do there is we can employ so-called Feshbach resonances, where we have two-component fermions, for instance. We can now fill them up to a Fermi energy. And then we make use of the fact that when these two atoms collide, they can actually jump into a different interaction potential. And we can now use magnetic fields, as also shown in the talk before by Letizia, with the magnetic field tuning of interactions, to bring this molecular bound state actually in resonance with the many-body environment, thereby very naturally actually enter the strong coupling regime. Now, what does this enable the strong coupling regime? If you think, for instance, about two-dimensional systems, as shown here, for instance, in an experiment by the group of Selim Jochen in Heidelberg, we can realize two-component fermionic systems where then in the strong coupling regime, which is over here, the superconducting transition, the analog of that, can be realized at critical temperatures which are up to 20% of the Fermi energy. Of course, in the solid-state material, this could easily correspond then to actual room temperature superconductivity. Unfortunately, typically to enter this type of strong coupling regime is a very challenging task in solid-state materials. And the question is how one could actually get closer to this regime. And here we have right now actually quite exciting times. In the last 10 years, the actually discovery of, or actually 15 years of van der Waals materials, these atomically thin materials like graphene, made it possible that we can actually think about entering the strong coupling regime. And I want to in particular focus on actually semiconducting materials in this regard. If you think about a semiconductor, like for instance, gallium arsenide, it's really a bulk material. With a laser, we can excite electrons from the valence band into the conduction band. And what we are left with is then a whole positively charged and a negatively charged electron, which attract each other. It's basically a hydrogen problem. Now, this we can, of course, solve. It will lead to bound states. However, these electric field lines, they will go through the material and thereby they are dielectrically screened. This reduces then the binding energy down to very small values of about 20 MeV for the so-called exciton bound states, electron hole bound states. So these don't even survive room temperature. However, if you think now about two-dimensional materials, in particular two-dimensional semiconductors such as transition metal dichalcogenides, an example is, for instance, tungsten diselenide. For the purpose of this talk, you can envision them to be basically graphene with a band gap. Then we have a different situation than in the bulk semiconductors. Namely, they are really atomically thin. So the electric field lines are actually outside of the material, they are not screened, and thereby we get much larger binding energies of the order of up to 500 MeV. But what that means is that the correct picture is actually to envision these excitons as a whole bound to an electron really tightly. It's a nice bosonic particle, which can fuel now like a nice point-like bosonic particle, much like those we have in cold atoms. Now, what is nice though is also that we can insert in addition electron in the system. These two will attract each other and form what is called a triene, the equivalent of our molecular states in cold atoms. The binding energy is about 30 MeV. Now, the next thing is we can connect our tungsten diselenate, for instance, to graphene gates and actually dope our material with additional electrons. What we will then end up with is, however, an electron gas characterized by a Fermi energy of about up to 50 MeV. But this shows already that now we enter potentially the regime where binding energies are comparable with the Fermi energies in the system. So by now, it seems that actually the strong coupling Bose-Fermi mixture regime is in reach in two-dimensional semiconductors. However, we face a challenge. What I show here is actually an experiment, well, part of an experiment in solid-state physics where two-dimensional materials is on this chip, and what is done is it's illuminated with this LED and the response is observed. The thing is, the materials are rather new, these transition metal chalcogenides, and we actually do not know all the properties. So we are challenged by knowing not exactly what is the role of phonons, what is the role of defects in these materials. So what would be nice to have a controlled environment to actually test which parameter regimes are the interesting ones for these new materials, so that we can actually realize new phenomena or functionalities in these materials. And here comes in actually our cold atom experiments. The idea is, instead of going to the cold atom laboratory and, for instance, studying paradigm Hamiltonians and study their fundamental properties, one can also think about really fine-tuning our system to actually model as closely as possible the desired solid-state material in question and actually learn what are the interesting parameter regimes to find a certain effect. So how would this work in practice? Let's suppose we have our two-dimensional material. We doped it with electrons. Now we shine with a laser on our material, excite excitons, and we are asking, well, can these excitons induce interactions between the electrons leading, for instance, to Cooper pairing? The question is, in which regime would this happen? Which kind of stacking do we need? Which kind of distances between different material sheets would we need? Well, for that, we could go then to our cold atomic system and actually relying on the concept of universality, realize the Bose-Fermi mixture or our ultra-cold atomic system and find, for instance, a temperature regime in which we find Cooper-induced in which we find pairing induced by the surrounding bosons between fermions, and then go back to our solid-state material and try to find exactly this parameter regime there. The thing is, this all sounds nice, but the question is really, how similar are these two systems really? Now, what we really need is then a translation manual from our cold atomic system to these transition metal chalcogenides, these atomically thin semiconductors. But what we do know is how to map fermions and bosons or our atoms onto electrons and excitons. We basically just take Bose-Fermi mixtures and choose these species to our liking. We know how to use lasers to generate two-dimensional sheets. However, the key question is, how can we translate the interaction mechanism between atoms on that of excitons and electrons in transition metal chalcogenides? So the question is really, is there a universal Bose-Fermi mixture Hamiltonian which can describe both cold atoms as well as these two-dimensional materials? And finding this effective universal Hamiltonian was really what was at the core of a recent work together with my postdoc Christian Fay, where we borrowed techniques from quantum chemistry to solve exactly the scattering problem of two electrons in one hole in the two-dimensional semiconductor. Now, using this exact diagonalization technique, of course, we can find the ground state of the system, but we can, which is the triene, which I discussed before, but we can also access all excited state in the system. Here's the full eigenenergy spectrum shown as a function or with increasing number of the eigenstates of the system. So we get these excited states, but these excited states, by looking at their wave function, we find that these exactly correspond to scattering states between electrons and composited excitons. And now we can do something which we are very much used to from cold atomic physics. We can look at the phase shift of these scattering states and plot it versus the energy. And now what we find is that there is actually a universally effective model for this scattering, which you can apply to both exciton-electron scattering, but also to cold atomic collisions by using the right phase resonance parameters. What we can do with this now is really to fill up this whole translation table. But the key take-home message is that the dimensionless interaction parameter, which compares the interaction energy to kinetic energies in cold atoms, can be made of the same value as it can be done in two-dimensional materials, although both systems live on vastly different energy and temperature scales. And this is really a testament to the concept of universality, that we can really describe often phenomena which take place in vastly different systems by the same underlying low energy. Hamiltonian actually, Tietze in her talk, made the step really from cold atoms to high energy physics. Here, the step is just about 10 orders of magnitude. Well, actually believing this translation table and this universal model, what we can do now is actually to try to explore the phase diagram of strongly interacting Bose-Fermi mixtures as function of the densities of fermions and bosons, and we can do this now jointly in cold atoms in 2D materials. So far, in fact, this phase diagram is not understood at all. And this is just an illustration of the possible phases which could be envisioned, reaching from supersolidity of bosons to actually induced superconductivity between the fermions, or the formation of dry and Fermi liquids. For theorists, of course, such a phase diagram is a feast. It features competing orders. There can be unconventional pairing, or higher order correlators might become crucial. However, what is really good for us theorists, we have now two complementary platform on which we can actually test our theories, cold atoms, as well as 2D materials. So where do we stand in the exploration of this phase diagram? If you want to understand this whole phase diagram, it's good to start from limits where we have good control over our system, and also good control also about our theoretical understanding. And what such limit is an extreme limit where a single boson is immersed in surrounding Fermi gas. And you might ask, how are the properties changed of the single boson, which then is basically quantum impurity, when it interacts with the surrounding environment of fermions? So one quantity to actually quantify that is the spectral function of the impurity. It tells us at which energy and momentum does the particle basically want to live. And if there are no interaction between the impurity and the surrounding system, this is just a p²/2m dispersion relation. The challenge is now to include the interaction with the environment and include fluctuations in the many-body system on all length scales. We achieve this by a computation functional renormalization group technique, which in stepwise fashion includes more and more fluctuations, starting from short distance scales to going to more and more long distance scales. And what I've shown you now is the corresponding RG flow of the spectral function. We start integrating out high energy modes, and by that, we change the spectral properties at high energies. But then also the polaron is affected at lower energies. This gets a downward shift in energy corresponding to attractive interaction. But also spectral weight is transferred to excited states in the system, so that in the end, we end up actually not only with one quasiparticle excitation, but actually with two instead of one before. So there's an emergent new quasiparticle when we enter the strong coupling regime, which is termed, or which we termed back then, the repulsive polaron state. Now, we can plot the spectral function at zero momentum as function of the attractive interaction energy. If you start at a very weak attractive interaction, we just have one quasiparticle excitation, an attractively shifted quasiparticle. But as we enter the regime where epsilon b, the bound state energy, becomes comparable to the Fermi energy, then we get an emergence of a new quasiparticle due to this interplay between few and many-body physics. And this emergent new quasiparticle was then observed a year later in cold atom experiments, both in 3D and in 2D, by the groups of Grimm and Köhl in Innsbruck and Cambridge. However, believing the concept of universality in our translation table, well, this should not only appear if I immerse, let's say, potassium atoms in the lithium sea, but also if I immerse an exciton in a doped semiconductor. And finding this type of physics was really at the core of a lot of work which Atachi Mamuklovinson at ETH Zurich put into 2D semiconductor experiments, where he dopes on purpose, for instance, molybdenum diselenide sheets with the electrons and observes the spectral response. And indeed, when he tunes now the dimensionless parameter epsilon f over epsilon b, he indeed finds two quasiparticle excitations, the repulsive and attractive polaron. And in the background, so his data is shown in red. In the background is the same theory applied to cold atoms now and the transition method Tiger-Coordinates using the input parameters from our translation table. So this really marks one of the first cases of what one could call an applied quantum simulation of 2D materials using cold atoms, where in effect first discovered in cold atoms is about half a decade later discovered then again in two-dimensional materials, where it can be now used to control the optical response of semiconductors. Now, this gives us some trust that we have a good model to describe this Bose-Fermi mixture phase diagram. And now we can start actually to go into the regime of finite density and to explore this phase diagram. However, I'm saying the word phase diagram. So here I'm talking about the ground state properties. It turns out that the Fermi polaron problem is a little bit more richer than what I was describing before. Namely, the interplay between few and many body physics leads to an additional effect, namely that at sufficiently strong attractive interactions, the impurity will not only collect democratically a polarization cloud surrounding it, but at some point it will say, actually, it's better for me to take just one fermion from the environment, build a molecule, push away the rest of the atoms, and live as a molecular quasiparticle. And this transition can be described with rather not too complicated techniques in 3 dimensions, and in a recent theory experiment collaboration with a group of Sagi at Technion, we were now able to in detail study this transition and really establish its existence in great detail in 3 dimensions. And this effort was really led by my PhD student Oriana Diesel, and as well as Jonas von Michewski. Now, in 2D, however, when we want to explore this case, which is more relevant for semiconductors, we meet a bigger challenge. It turns out that the same approximations which worked in 3D will not work anymore to describe this transition. Indeed, the bound state will be destroyed basically by the Fermi pressure of the environment. However, it will be restored when one includes 3-body correlations in the calculation. So we need a technique which can treat 3-body correlations. At the same time, unfortunately, and so to say, the molecules which are formed consist of a boson and a fermion, so they're fermions, meaning we cannot describe them with the mean field theory. So we have to have now a theory which can describe 3-body correlations as well as going beyond typically mean field theories. And this is done again by the functional renormalization group technique. And using that, we can now go actually to find a density, and we predict the formation of a molecular liquid phase, which is a Fermi liquid, which transitions over into a phase where we have polarons, bosons stressed by environment fluctuations. And since these are bosons, they can condense. And what they, however, do is they have an interesting back effect on the surrounding Fermi gas. Namely, the fermions will not be hybridized between being fermionic particles and molecular particles, although one is not even in the regime where actually the molecular liquid exists. So they are actually precursors of molecules already in this polaronic mixed phase. Now, these predictions so far have not been observed, neither in cold atoms and nor in 2-dimensional materials. In particular, in those, it's a challenge actually to keep the steady state using a laser which will excite continuously excitons in the system. And so the race is basically on to observe these effects, and we will see who will do it first in cold atoms or 2-dimensional materials, or to see if the theory is wrong, and then we have to actually adjust again our thinking about these possible phases. Well, I said that it's really hard to describe this phase diagram in general. And the reason for that is actually found when we go to the opposite limit, namely when we insert just a single fermion in the Bose gas. What we showed in this case is, well, one might expect, or what was presumed to happen is, well, this is an impurity in the Bose gas. This should be described by just an impurity interacting with phonon degrees of freedom, like in the Fröhlich model shown here in the first line. When impurity just interacts linearly with the excitation of the surrounding bosonic environment. However, what we then found is that if one enters the strong coupling regime, a new RG relevant term appears in the action which corresponds to the constant rescattering of phonons. And this has now to be taken into account, which then leads, however, to a change in the spectroscopic response of the system, which will then strongly deviate from the predictions of the Fröhlich model. And these predictions were then verified in experiments independently by Eric Cornell and Debbie Jin at Gila, as well as Jan Alt at Aarhus University, concerning the energy which we predicted in our QFT approach. However, in the last years, it turned out that there are more open questions actually in this scenario as there are actually answers. If one really looks into the detailed spectroscopic response in these systems, and this is shown here as the blue data dots, what the experimentalists found is a very strong broadening of what is supposed to be the polaron response. And the question is this an experimental artifact, or is this actually something intrinsic? If one compares this actually to theoretical predictions using variational wave functions using 1 or 2 particle excitations from the BSC, where the energy fits quite okay, but the line shape is certainly off. When one includes, on the other hand, infinitely many particle excitations in the coherent state ansatz, then one finds that there's a prediction of intrinsic broadening of the spectral response, but it's still not conclusive if really the observed effect was actually an intrinsic many-body effect or not. Moreover, this theory, which describes well experimental data at first sight, also predicts some interesting states where it's not so clear what the physical significance is. Namely, what happens in the predicted response. Here is actually the interaction shown at the interaction regime shown here. At actually large attractive interaction, the same theory predicts that if there is a bound state between the boson and the fermion, then this bound state can not only be occupied once, but actually twice, 3 times, many times, leading to a basically staircase of actually peaks in the spectral response, which raises the question, are these multi-body bound states really physical? And this brings me to the last part of my talk, where we are asking, or which describes our work, we are asking now, what is really the impact on higher order correlations on this Bose-Polaron problem? If you think about multi-body bound states, this certainly has to do with actually many particles talking to each other on rather short distance scales. So what is the impact of higher order correlations? This is really what we work on with Arthur Christian, who is a PhD student in my group and one of Ignatius Chirac. If you think about multi-body bound states, there's one scenario which is rather easily understood, and this is the one which I described before. Let's assume there's a bound state between the red particle and the blue particle. One can envision that the second particle just falls into the same bound state and builds a 3-body bound state. Basically, these 2 particles don't even have to talk to each other in this case. However, what Vitaly Efimov showed in the context of nuclear physics in the 70s is that this is not the only requirement or the strict requirement needed. In fact, even if 2 particles don't build a bound state, their interaction can already be still sufficient. If a third particle comes along, then the red particle can induce such strong correlations between the 2 blue particles that the whole 3-particle complex can become bound. And these are so-called Efimov states. Of course, this is definitely relevant for the Bose-Polaron problem. And the question is really, how does this few-body aspect influence the many-body physics of polarons? On the other hand, we can think, however, about the question, well, if the red particle is stressed via Bose-Polaron tracing, does Bose-Polaron formation actually also influence few-body physics and the existence of these bound states? Now, to tackle this question, though, about this interplay between few and many-body physics, we need to have an approach which can do 2 things. Number one, it has to treat infinitely many excitations from the Bose gas to treat correctly Bose-Polaron formation. At the same time, it has to solve the 3-body problem exactly. So to tackle this problem, we have to somehow simplify our situation. And we do this by going, instead of working in the lab frame, going to the co-moving frame of the impurity. Now we know exactly where the impurity is. And this eliminates the impurity operator from the problem, but we buy ourselves a non-local boson interaction, which we have now to treat. What we win is, again, that instead of having to treat full 3-body correlations, it's already enough to treat 2-body correlations exactly, because we know exactly where our impurity is. To treat those 2-body correlations now exactly, we have to extend the coherent state approach, which was developed before, to actually account for a Gaussian state contribution. And this is really using techniques developed more in the context of quantum optical systems. And this really can account now for exact pairwise boson correlations and include arbitrary many excitations in our calculations. Of course, when we go to really low densities in our calculations, maybe then we should recover the physics observed in laboratories at very low density, namely observing the Efimov effect. And indeed, our theory then predicts correctly the Efimov effect, the formation of a 3-body bound state here shown, its energy versus the inverse scattering length, the 3-body bound state which exists in absence even of 2-body binding. And we calculate we can predict then the scattering length at which this happens for actually typically experimental setups which are realized throughout cold atom laboratories. But then we can increase density and ask what happens to this many body F-MOF states. Is there a 4-body, 5-body, 6-body, 7-body, 8-body, 10-body bound state? And indeed, as we increase density, we find a larger and larger bound state clusters containing 4, 10, 20 body bound states. And this we can now actually quantify a little bit more exactly. So let's assume we have a negative scattering length. In a few body regime, we would not have a bound state. But if we only insert enough particles, so this is shown scattering length versus particle number, average particle number in the system. If you only insert enough particles, we find bounding becomes possible. But then something peculiar happens. If I have a bound state and then I throw in one more particle, the binding energy per particle increases. So the more particles I have, the easier it becomes to bind. And we call this effect a cooperative binding effect, actually a name borrowed from the chemistry, for instance, of molecular assemblies, where, for instance, hemoglobin can bind oxygen. The better, the more oxygen is already on the hemoglobin molecular assembly. Of course, at some point it stops, but it's basically brought from that. And what this, however, predicts is for our, so to say, poor Bose-Polaron, if you throw in our impurity in our many-body system, actually, as soon as the first particles start to bind, even more will bind, and this process never stops until actually our single impurity rules all the atoms and builds a gigantic cooperative F-MOF cluster. Now, this, of course, would basically vanish right away due to chemical reactions. So it seems like, wow, now our Bose-Polaron has found its end. But the question is even actually, can the Bose-Polaron itself still survive, namely in terms of an excited metastable state? So basically, is it still possible that on transient timescales, a Bose-Polaron can exist by forming a polaron cloud on top of a constant background density, at least for a certain time? And to answer this question, we now solve our problem by scanning the energy of the system as function of the number of particles inside a polaron cloud, where we fix the background density of the system. If you have a very large number of particles in the polaron cloud, it will decay towards this cooperative bound state. There's no escape. But we find that there's a local minimum which actually will permit the existence of a metastable polaron, which is actually protected by a barrier which is repulsive and which gives a finite lifetime to the Bose-Polaron. Now we can plot the energy of this metastable polaron as function of the inverse scattering length. And we find that this repulsive barrier is active actually for quite some interaction regime. Of course, at long time scale, it will decay into the deeply bound cooperative F-MOF cluster. However, at some finite interaction strength, this repulsive barrier will vanish and the particle will decay. And this critical scattering length itself is density dependent, and a low density will reduce to the normal F-MOF resonance, A-, where actually in experiments one observes the effect that one has one impurity, two bosons come, they collide with impurity, forming a deeply bound state and performing three-body recombination. Now this value is changed into AC, which you can view basically like the possibility of having three-body recombination changed by polaronic dressing. So it's kind of, you can view it as polaron dressing changes the quantum chemistry of three-body combination, because if particles scatter off a polaron, there are already bosons there which can lead to actually efficient decay. So basically this is a modification of the few-body physics due to many-body fluctuations. With this, let me come to the end of my talk, where I hope I could convince you that now it's an exciting time to actually study this Bose-Fermi mixture phase diagram in detail, and first steps have been done, in particular in the low density regime. And it's a nice playground to bring together cold atomic physics and 2D material research. However, what it really highlights is the power really of cold atom quantum simulators, which can help us to actually see really new phenomena, which can then actually a couple of years later be observed, for instance, in solid state materials. As we have seen in the last part, though, it also helps us to guide really our theoretical understanding and see, for instance, where actually many body fluctuations are important, or higher order correlators become important, really serve as a benchmark for our computational tools. Now, finally, we can also ask, can we turn actually everything around? Can we also use our transition method high-grade coordinates as a platform for solid state-based quantum simulators? And also we are working in actually this direction, and we have recently shown that actually TMDs are a nice platform by using interfacial excitons to study the low-dimensional physics of dipolar systems, where it seems like that one can enter actually the regime where even dipolar Wigner crystals could be reached, and interaction strength, this is so far a challenge in ultra-cold atoms. Similarly, our friends at RichardSchmidt Institute showed how we can use ion bombardment of TMDs to actually write structures on the TMDs to build, for instance, a platform to study exciton physics on these systems. And there has also been progress in how we can use excitons to sense, for instance, electron correlations. And we have made also first steps towards reaching tunable electron-exciton interactions using interlayer Feshbach resonances. With this, let me finish my talk, and I hope that I could convince you that it's now an exciting time to bring together 2D semiconductors and cold atoms. And there are interesting aspects in the interplay between few and many body physics and Bose-Fermi mixtures, where even actually polarons can now change how we can view actually quantum chemical processes. And finally, there is the venue of solid state-based quantum simulation using 2D materials, where the biggest advantage is most likely that number one, we can reach interaction regimes not attainable before. However, more importantly, the energy scales of semiconductors is so much higher so that duty cycle times are much reduced. For instance, giving the which would give the perspective to have much faster data acquisition, as for instance, it is possible with ultra-cold atomic systems. And with this, I would like to thank you, and most importantly, to thank my group. Without, of course, all this work would not have been possible. Thank you.
All right, thanks a lot, Richard, for this exciting talk and covering real materials and the world of quantum simulations and ultra-cold atoms, and showing how they really nicely connect and stimulate each other. Okay, so if you have questions, let me remind you that you can post them in the Slack channel. There's one question already, Richard. So what parameter controls the validity of the Gaussian state approach in your description of Efimov bound states?
Okay, the question is basically the validity of the bound states you obtain. So the thing is, a Gaussian state has exponentiated operators. So basically we have e to the b dagger b. If you want to describe a three-body bound state, well, you have to have b dagger, b dagger, b dagger, so just three particles. So what you have to ensure is that your density, which is the control parameter, is so low that in the superposition state of various particle sectors, you actually project out basically only the three-body sector. So the control parameter in this case to get the Efimov states is the density itself.
Okay, yep, so okay, here's another one. Hi, thanks for the great talk. Should one take into account the modification of the scattering properties of the bosons in the bosonic cloud around impurity, i.e. is the scattering length of the repulsive boson-boson interaction dependent on the polaron cloud?
Several points to this question. It's a very good question. Number one, the boson interaction is absolutely crucial to lead to the ultimate stability of the Hamiltonian and make it bounded from below. Strictly speaking, we get an unbounded situation here in the energy with our cooperative binding. These polaron clouds would be stabilized by repulsive interactions, as asked in the question. The next question is actually, would the scattering length maybe itself change within maybe or due to the polaron cloud? That's an interesting question. We have now conditional correlations surrounding the impurity, and you could ask for, are there many body changes to the scattering length due to the increased density in the polaron cloud? Yes, if you could derive something like a scattering phase shift in the medium close to the impurity, you would see a change in the scattering phase. At a normal conference, I would ask now back if that is what the person was asking, but we can't do this here, I guess.
We can't do this.
So we can do this at the table later.
Right. Let me remind you, actually, that's a good point to remind that we have our discussion round now also coming up. So please join us also for the discussion round. Yeah, I think we're basically at the end of the session of this session. So thanks to our both speakers, Laetitia and Richard, for these really two exciting talks. And please join us in the discussion session now, and looking forward to seeing you there and discuss a bit further with us. Okay, so thanks Laetitia and Richard, and see you in the discussion room.